Hi, this is Dr. Anthony Revis, and this is SVSU General Chemistry 111, Chapter 4, Lecture 3. That's Lecture 3 of Chapter 4, Stoichiometry and Chemical Reactions. We will cover writing and balancing chemical equations, classification of chemical reactions, reaction stoichiometry. We will also look at reaction yields and quantitative chemical analysis. These topics will be covered, however, they might not be covered in this order. In this lecture, we will look at ionic species in chemical reactions. And this is important because many chemical reactions take place in aqueous media. In aqueous media, ions may be formed. When ions are involved, the chemical equation may be written with various levels of detail. In other words, an ionic reaction, or at least ionic species in a chemical reaction, require a bit more attention to detail because of the ions. So if we wrote a molecular equation for a calcium chloride, it would be shown as we have it right here. We would have the aqueous form of the calcium chloride, the aqueous form of the silver nitrate, going to give the calcium nitrate and the silver chloride. However, molecular equations don't explicitly represent the ionic species that are present in the equation. Now, as we talk about ionic species, you will want to pay attention to the AQ nomenclature, the solid nomenclature, the liquid, the gas. In other words, you will want to pay attention to the physical state of the species. When ionic compounds dissolve in water, they may dissociate into their ions. And what does that mean? Here we show you some examples. If we take calcium chloride in water, in aqueous media, it will produce calcium plus 2 ions, plus chloride minus ions. And as with molecular equations, ionic equations must be balanced for the atoms, but they also must be balanced for the charge. So in this case, we balance the atoms and the charge by adding a 2 in front of the chloride. In a similar fashion, we have silver nitrate that dissolves to form silver cations plus nitrate anions. Notice that they both say AQ. That means that it is soluble in the aqueous phase. We notice also we have a balance of the atoms as well as the charge. In the case of calcium nitrate, we do likewise. We have a balance of the charges and we have a balance of the atoms when we add a 2 in front of the nitrate anion. Unlike these three ionic compounds shown above, silver chloride does not dissolve in water to any significant extent. In other words, you'll have a salt, an ionic compound, that does not dissociate into its ionic species in water. That is the case for silver chloride. Silver chloride AQ does not give Ag plus AQ plus Cl minus AQ. Okay? That's because it forms a precipitate. One of the features of the ability of a compound or substance to form ions in solution is that it will conduct electricity. It will conduct a current. When a compound is capable of conducting electricity or current, it is called an electrolyte. So, an electrolyte is a substance that produces an electrical conducting solution when dissolved in water by forming cations and anions. In other words, if it is soluble and it produces ions, it will conduct electricity. Now, some of that conduction will be low, will be slight conductivity. Some will be very high. But in general, ionic species in water conduct electricity. This is true for ionic compounds as well as acids and bases that you will learn about a little bit later in this lecture. So, how do we manage these equations? How do we write these equations? Explicitly representing all dissolved ions results in what's called a complete ionic equation. So you have to write what's called a complete ionic equation. So what do? In the case of calcium chloride plus silver nitrate, we write them on the left side equation as AQ. What we discover is that when we get to the right side equation, silver chloride, which results from this reaction, produces silver chloride, this double displacement reaction. So we have it where the two chemical species are represented in identical forms on both sides of the arrow. You have calcium plus 2 and NO3 minus because they are both AQ. All right? However, notice that the silver and the chloride have combined to give a solid material. All right? Make a note of that. Watch what happens. Follow it through. The calcium plus 2 and the NO3 minus are what are called spectator ions. These ions, the spectator ions, they're there for the electronic neutrality, but they're not changed in the process. So, when we write a balanced or complete net, or a net in this case, ionic equation, we eliminate the spectator ions. So elimination of the spectator ions gives us a net ionic equation. So let's recap that again. The complete ionic equation is written by showing each of the AQ species in the reactants as ions. Once those ions react, they come together, forms a solid. The solid precipitates. We then cancel out the spectator ions, which will be the ions common on the left and the right, follows the rules of math, and we're left with only the species that will give the precipitate. That is what doing complete and net ionic equations about. The complete equation is to write them all. The net is to write the one that only forms the solid. So basically, you keep ions that precipitate. Okay? Basically, we like to talk about it as eliminating spectator ions. But the other way of thinking about it is you keep the ions that precipitate. Okay? So the net ionic equation, again, will result from the ions that form a precipitate. So, silver plus chloride then is an example of a precipitation reaction. A precipitation reaction is one in which dissolved substances react to form solid products. So, when a solid product results from the combination of two aqueous solutions, that is called a precipitation reaction. Precipitation reactions are also known as double displacement or double replacement or even metathesis. So these are terms that are used to describe this type of process, this precipitation reaction. Many reactions of this type involve the exchange of ions between ionic compounds and aqueous solutions. So this is what you'll see happening for these types of reactions. Precipitation reactions are common in nature and in industry. An example of an industrial process would be where calcium chloride and potassium hydroxide is used to form calcium hydroxide. It precipitates out. You add in the aqueous calcium chloride and aqueous potassium hydroxide, and you get the solid calcium hydroxide. Again, calcium chloride aqueous plus potassium hydroxide aqueous gives you the calcium hydroxide. So let's take a look at another example. Take a look at the precipitation reaction of sodium chloride with silver nitrate that yields solid silver chloride. The silver chloride precipitates from the solution, which is consistent with the solubility rules, which we will be examining. So the solubility rules dictate the degree of precipitation, or actually which species will precipitate from a solution. So when we carry out this reaction, the net ionic equation is silver plus chloride to give silver chloride. And you can immediately get that or see that by examining the product that is solid. Which ions give the solid product? That's what you're looking for in a net ionic equation. This could also be examined by writing the complete ionic equation as we show you here. Cancel out the spectator ions and you're left with the silver and the chloride as the ions that form the precipitate based again upon the solubility rules. A second example is when we take potassium iodide and lead 2 nitrate. Lead 2 nitrate and potassium iodide form a solid lead iodide, lead 2 iodide, plus potassium nitrate, which is aqueous. So if we walk this through to write a net ionic equation, it is shown here where the lead plus 2 combines with 2 molecules, 2 atoms of I minus in aqueous solution to form the solid lead 2 iodide. This can also be seen by writing the complete ionic equation and canceling out the spectator ions to leave you with the precipitate. Not all ionic compounds are soluble in the aqueous phase. So now, what is solubility? So let's look at a few simple definitions. We're talking about solubility and precipitation reactions. All right, solubility. Solubility is the maximum concentration of a substance that can be achieved under specific conditions. In other words, there's only so much of the solute that can be dissolved in the solvent. The solute is the item being dissolved, the material being dissolved, composition of matter being dissolved. That's the solute being dissolved in the solvent. And I say water, but it could be some other one. But in the cases we're talking about here, it's an aqueous solution. So that's solubility. Substances that have a relatively large solubility are said to be soluble. So if they have a large solubility, they're soluble. In other words, sugar in water is soluble. Salt in water is soluble. Okay? A substance will precipitate, however, when solution concentrations are such that the concentration exceeds its solubility. In other words, there is a maximum amount of solute or salt or sugar that you can put in the water. There's a maximum amount. Most of these definitions, by the way, these are terms you already really know. Okay? So don't sweat it. If you understand the definition already, you're good to go. Substances that are relatively low solubility are said to be insoluble. And these are the substances that readily precipitate from a solution. Okay? All right? So, in other words, if it's not really soluble in it, it'll basically just plate out, fall out right away. All right? So let's recap. A substance will precipitate when the solution concentrations are such that its concentration exceeds its solubility, when it passes that point. Substances that have relatively low solubility are said to be insoluble. These don't go in. They basically, as soon as you drop it in the water, it just falls out. Okay, it doesn't ever really go into the solution, into the aqueous phase. There are some helpful rules to govern whether or not a material is soluble or not. You do well to memorize these rules, find your own way to memorize them. But there are some trends that will help you know or guess whether or not it's soluble or not. For example, if it's in group 1, you can guess and assume that it's going to be soluble. Group 1 and ammonium ions are soluble. If it's in group 17, it's soluble, and there are some exceptions that we'll show you. But if it's in group 17, your first guess is that it's soluble. Also, there are some polyatomics that you want to be aware of, take a look at, memorize, that are soluble. Now, some are slightly soluble, but for the sake of this level of chemistry, we're really going to talk about them being soluble instead of differentiating really heavily whether they're slightly soluble or not. If the differentiation is needed, we'll bring that to your attention. Okay? So those are soluble ones. The insolubles, we show you right here. Basically, again, you have to memorize and find your own way to do it. They're halides and these 3. Then you have the sulfates are insoluble for these 6 ions shown here. Okay? So basically, again, you'll have to memorize those. Then you have this group that are just insolubles. The hydroxides are insoluble. The chromates, the phosphates, carbonates, sulfides, insoluble. Then there are some soluble exceptions, so take a look at it. Compounds of insoluble ions of group 1 metal ions are ammonium ions. There's some exceptions that you want to be aware of. Hydroxides of group 1 metal cations and barium plus 2. Just be aware of those. Find a way to memorize them or have some trends that you can refer to help you remember them. So let's practice solubility and at the same time take a look at molecular, total ionic, and net ionic equations. In this slide, we show you 4 examples. The molecular equation for silver nitrate and potassium chloride is shown. When that undergoes a reaction, it forms silver chloride and potassium nitrate. Note that the potassium nitrate is aqueous and silver chloride is solid. If you take a look at the net ionic equation, we've noted that silver chloride is not soluble because even though halides are soluble, the exception to the solubility rule is for silver. Therefore, silver chloride forms a precipitate. Note also in the net ionic equation, we cancel out the spectator ions and we're left with the net ionic equation. Similar process follows through in 2, 3, and 4. Note that in number 2, carbonates are insoluble. Therefore, the magnesium carbonate forms a precipitate. In the case of number 3, sulfates are soluble. However, cerium is not soluble. Number 4 shows another carbonate, which is insoluble. So this is how you will work the problems through for a molecular equation, total ionic equation, and net ionic equation, and also how you would know which forms a precipitate. Precipitates form when the forming ions are insoluble in the water phase. Understanding the principles of solubility is helpful in designing some quantitative analysis techniques. A gravimetric analysis is an example of that technique. Okay? So what's a gravimetric analysis? A gravimetric analysis is when we dissolve an unknown substance in water, then we act that unknown substance to form a precipitate. In other words, we take a soluble substance and then we add another reagent to it, and that reagent precipitates out another compound. Okay? Then we take that compound, you filter it and dry it, dry the precipitate. weigh the precipitate, then use the chemical formulas and mass of the precipitate to determine the amount of the unknown ion. Now, we're going to show you how you do all this. Trying to think through the rules and trying to memorize them is not what we're really intending to do with you here. But the bottom line is this. You take a soluble compound, you add another compound to it, a new compound that's the precipitate falls out, you collect that precipitate, dry it, weigh it, and then you use the rules of math, chemistry math that is, to determine the original soluble solution. Okay? And we're going to show you exactly how to do that. So let's take an example. Again, this is gravimetric analysis. And it's a quantitative method of determining the ions from which the compound was derived. Okay? So you have a 0.566 gram sample of an ionic compound containing chloride ions. So you know chloride's in there. And an unknown metal is dissolved in water and treated with an excess of silver nitrate. Now, the silver nitrate is the precipitating agent. So when you add it to this, it's known that the chloride of silver is insoluble. So when you add the silver nitrate, which is silver plus and nitrate minus, the silver will combine with the chloride to make a precipitate of silver chloride. Okay, and that's what's happening in this reaction. All right. If 1.0882 grams of silver chloride precipitate forms, that's the new substance formed, what is percent by mass of chloride in the original compound? So we're going to do a backtrack calculations to get to our answer. Here's what we know. We know percentages equal to part over the whole. We know our whole was 0.5662 grams. What we need is the mass of chloride. That mass of chloride is related to the mass of chloride in silver chloride. And so by determining the composition of the silver chloride, we can now figure out how much chloride was there. And we do this by using percentages and things we've already shown you. So here's how it works. Here's the solution. First, we need the molar mass of chloride in silver chloride. Okay? So we have 35.45 grams of chloride, and we have 143 grams per mole of silver chloride. Therefore, we have 143 grams. Okay? So we can take the percentage. And so we have the 35 grams divided by the 143 grams. We calculate the numbers, and we get 24.72%. Now, we know we collected 1.0882 grams of silver chloride. So if we take the percent of silver chloride as a decimal, 0.2472, times that value, we discover that we have 0.26 grams, approximately, of the chloride in this sample. So we then take the chloride grams, 0.2690 grams, divided by 0.5662 grams. We do the calculations, and we discover that the percent chloride in this original solution was 47%. That's how much chloride was in the original solution as an ion. Now, let's start to talk more about some other reactions that are related to ions or that involve ionic type chemistry. Acid-base reactions involve ionic or ion type chemistry because many of the acids, when dissolved in water, will form ions. So let's talk about them. An acid-base reaction is one in which a hydrogen ion, an H+, is transferred from one chemical species to another. Essentially, a acidic proton, H+, will be transferred. That's how an acid-base reaction occurs. And it transfers to the basic compound or the more basic compound in the reaction. An acid is a substance that will dissolve in water to form hydronium ions, H3O+. In other words, when a hydrogen ion is liberated from the acid, it immediately combines with water to form H3O+ called a hydronium ion, leaving a counter ion. In this case, the example shown here, HCl plus water, gives it a counter ion of chloride minus. So in this solution, we essentially have chloride minus ions, and we have H3O plus ions. This is an acid-base reaction. Hydrogen ions are transferred from HCl molecules to the water molecules. The HCl acts as an acid. The water acts as a base. Water, in many instances, will act as an acid, and then others, it will act as a base, and it will depend on the other species. Okay? So be aware of that. We show you here a table of common acids. The expectation would be that you memorize these and be familiar with them and their names. Acids that completely react in water are said to be strong acids, and these are strong acids, meaning that each of these acids will supply a proton, an H+, to the water solution to form a hydronium ion with the water. Okay, so you'll get H3O+. Virtually every HCl molecule and every other strong acid that dissolves in water will undergo this reaction. So they all dissolve, is the bottom line, in water. They all form very good hydronium ions. Okay, and at the same token, that makes them very good electrolytes. Electrolytes are species that produce charges in water. So if you hear the term electrolyte, strong acids form good electrolytes. Strong salts, strong ionic compounds form electrolytes because they dissolve completely in water. And when they dissolve completely in water, they allow transfer of charges through the water. So that's what an electrolyte is. A neutralization reaction is a specific type of acid-base reaction in which the reactants are an acid and a base. The products are often a salt and water, and neither reactant is the water itself. So you get it? So when we talk about neutralization, we don't consider water as a reactant in the process. Okay? So here we go. So we have this base, magnesium hydroxide, showing an example, plus HCl. Notice that we balance the equation with two atoms, 2 moles, 2 molecules of HCl. 2 is the coefficient. That coefficient is now available to be used in a conversion factor problem. So now we produce magnesium chloride and we produce water at 2 moles. So now, the acid in most cases can be easily identified by looking for the hydrogen. The compound that has the hydrogen is typically the acid. Now, that doesn't mean other compounds don't have hydrogen, but where the hydrogen is bonded will tell you that. So you memorize the acids, the strong acids, so you can readily identify the acid. The base is going to be the other material, or the material that has a hydroxide, or the material that has a higher pH. In this case, we have the acid HCl, and we have the base as magnesium hydroxide. These will then go to what's called the conjugate acid and the conjugate base. And the acid will go to the conjugate base, and the base will go to the conjugate acid. So the conjugate acid is the acid formed from the base, and the conjugate base is formed from the acid. You get it? Now, when we talk about these conjugate acids and conjugate bases, keep in mind that the arrow for strong acids and strong bases lie to the right in neutralization reactions. Therefore, the conjugate acid or conjugate base may be in a weaker form. A type of neutralization reaction that is carried out in what is called quantitative analysis is titration. So what is a titration? A titration involves two solutions. One solution is called a titrant. That solution contains a known concentration of one of the reactants. The other is an analyte. That solution contains a reactant of an unknown amount or concentration. And the goal of the titration is to determine the unknown amount. That is determined by carrying out the reaction and analyzing the results at what is called the equivalent point. So, measuring the volume of a titrant solution required for complete reaction with the analyte is the equivalent point, which allows for those calculations of the analyte concentration. In the diagram shown here, we show you a burette, which is mounted above an Erlenmeyer flask. In the Erlenmeyer flask is one of the materials, the analyte. In the burette is the other material, the titrant. And that titrant is added to the flask until there's a change in the color of the analyte in the flask. Now, that color change occurs because there is an indicator to tell when there's a change from acid to base. So, indicators are added to the analyte for a change in color at the equivalent point. The volume of the titrant measures that endpoint, which is for all practical purposes in general chemistry, the equivalent point. So, for all practical purposes in Gen Chem, we consider the endpoint to be the same as the equivalent point. And we base that upon the volume that has been added to the flask when the color changes. So once we carry out a titration, we can use some straightforward math to determine the unknown concentration. So let's do that with an example. Here it is. A 25.0 ml sample of a solution is analyzed for its sulfuric acid concentration. It takes 46.8 ml of 0.661 molar sodium hydroxide to neutralize the sample. Find the molarity of the acid. A couple of things should be noted here. We know that we started with 25.0 ml of a sample. We know that it took 46.8 ml to neutralize it, but what's very important is not just 46.8 ml, but it is 46.8 ml of a specific concentration of sodium hydroxide, which is known to be 0.66 molar. And we know that molar means moles per liter. So the number of moles of sodium hydroxide in 1 liter is 0.661 moles sodium hydroxide in a liter. So let's look at how we solve this. We start with sodium hydroxide plus sulfuric acid, and that's neutralized to make the sodium sulfate salt and water. We note that we have balanced the equation by placing a 2 in front of the sodium hydroxide and a 2 in front of the water. So we have a balanced equation. So we now can take a look at the givens, and we have them. We look at what we want to determine, sulfuric acid, and we note again that there are 0.661 mole of sodium hydroxide in 1,000 mils or 1 liter. So, to carry out this calculation, we set up a dimensional analysis, starting with our given of 46.8 mils sodium hydroxide, because that's the amount that it took to reach the equivalent point, the end point, where the color change occurs. So we have mils. Therefore, we do a cross bar, mils on the bottom, sodium hydroxide on the bottom, and moles per mil on the conversion factor because we have mils in our original 46.8 mils of solution used. We then carry that through to another conversion factor, crossbar moles on the bottom of sodium hydroxide, and we know the relationship between moles of sodium hydroxide to sulfuric acid is 1 to 2. We set that up, and we now have the moles of sulfuric acid. So, in a problem like this, you will approach it by considering it as two problems. We are essentially first looking for the moles of sulfuric acid. Now that we've attained those moles, we know the standard formula for molarity is moles per liter. We would then take those moles and we put them on the top, and we know that it was 25.0 mils of the sample of the solution. We put that relationship and then we convert it back to liters by using 1,000 mil per 1 liter. And that gives us a final molarity of 0.620 sulfuric acid. So this is how we would carry out any of the standard titrations. It should be noted, you could have worked this problem by converting the mils to liters, the 46.8, converting it to liters. It would have worked out just as well. And you could have done likewise on the bottom. Could have taken the 25.0 mils and converted that to liters, and it would have worked out fine. As long as the unit analysis works out and it is done by a conventional dimensional analysis process, you will get the proper answers and it will be accepted in most Gen Chem classes. Okay? So there you have it. That's how we do a titration to determine the amount of an unknown. This is known as quantitative analysis. Now, we've talked about these strong acids. There are also species known as weak acids. The classical weak acid is acetic acid, which is in vinegar, which is the acid of fruit. So if you take the weak acid, acetic acid, and react it with a weak base, water, it will form conjugate base and conjugate acids as well. Now, oftentimes we don't think about it as strongly when we talk about this chemistry of conjugate acid, conjugate base, but the bottom line definition for a conjugate base is that it is formed from the acid. The bottom line definition for a conjugate acid is it is formed from the base. So you want to think of that as you think of acid and bases and be aware of it as you work through problems. Okay? Neutralization allows an acid and a base to react to form a neutral material. Weak acids, however, are in equilibrium. They don't dissolve as well. Okay? In other words, it does not form as many of the ionic species as a strong acid. So that's a differentiation between weak acids and strong acids. Weak acids do not give the electrical current values that strong acids give because they don't form as many ions in solution. So if you have acetic acid, reaction with water as the base in this case, you form the conjugate base and the conjugate acids here. And only about 1% of acetic acid molecules are present in an ionized form. So it's very weak. There, it's a double-headed arrow in the equation that denotes the partial reaction aspects of this process. So it's really partially reacted. So it's really not forming very many of the ions. This is also an acid-base reaction used for pH buffers. So weak acids are used in buffers. Weak bases, similar discussion as we had with the acids. Some compounds produce hydroxide ions when dissolved by chemical reaction with water. In all cases, these compounds react only partially and are classified as weak bases. So when you see an equilibrium arrow, that means it's partially dissociated. A single-headed arrow means it's going to the side of the pointed head arrow. So in this case, we have a weak base in ammonia, and we have an acid. Water is, in this case, it's acting as the acid. We form the conjugate acid and conjugate base, but only weakly so. Keep that in mind. There's not much dissociation in weak acids and weak bases. All right. So this is an acid-base reaction where the H plus is transferred from water molecules to the ammonium molecules. So in this case, the proton is on the water, and that proton is released and forms a conjugate base, hydroxide, but only weakly so because it is a weak base. Another type of chemical reaction where understandings about ions proves to be useful is in oxidation-reduction reactions. In an oxidation-reduction reaction, known as redox, electrons are transferred from one substance to another. If one substance loses electrons, another substance must gain electrons. Therefore, we call it oxidation-reduction, redox. If oxidation happens, reduction must happen. If reduction happens, oxidation must happen. In the case of oxidation, it is defined as the loss of electrons. Keep in mind, electrons are negative. So if it loses electrons, it becomes more positive. Reduction is a gaining of electrons. Again, since electrons are negative, we gain electrons, it becomes more negative. So we show you in the diagram here where an electron from A, which is being oxidized, is transferred to B, which is being reduced to form an electron deficient A and an electron enhanced or richer B. On the periodic table, some notable trends are important. Metals tend to undergo oxidation. Nonmetals tend to undergo reduction. Okay, so that's a trend worth noting. So be aware, in general, if it's a metal, it will very likely undergo oxidation. If it's a nonmetal, it will very likely undergo reduction. Metals become more positive, nonmetals become more negative. Here's some examples. When we oxidize sodium, it becomes sodium plus an electron. When we oxidize calcium, it becomes calcium plus 2 electrons. In this diagram, the oxidized form is shown on the right and the reduced form is shown on the left. So if we take bromine, it would undergo reduction. Br2 would undergo reduction and would move to the left side and become reduced. If we take iron plus 3, that's iron in an oxidation state of 3, if it gains 1 electron, it will be reduced to Fe plus 2. You'll have to get used to being able to note the direction of arrows and flow of electrons. One way to get used to that is simply to read the text, look at it enough times until it kind of starts to make sense to you. The key is to recognize that electrons are negative, and if you do the math and write a math equation, you'll be able to see that. Okay? Any atom in its elemental state, meaning an atom on the periodic table, has an oxidation state, a charge of 0. So in its elemental state, atoms have charge of 0. The elements on the periodic table are elements in their elemental state, therefore they have 0. But note that group 17, the diatomics are written as 2, as dimers. Bromine B is not written as Br, it's written as Br2 with a 0. Similarly with nitrogen and oxygen. So that's how diatomics exist. The elemental state of bromine is Br2, 0. Fluorine, Fe2, 0, and everything in group 17. And then you have nitrogen and oxygen. So be aware of the polyatomics. Okay, their zero state is a dimer, as a 2 at the bottom. Oxidation states, charges, for elements in a compound must be mathematically determined based on standards. The sum of the charges must equal the charge on the compound. In many cases, for compounds that are neutral, it will be 0. In fact, for all compounds that are neutral, the charge must equal 0. When there are polyatomic ions carrying charges or compounds carrying charges, the sum of the charges must equal that value. There are certain standard groups and certain elements. You learn them as you go. But we'll point out to you, group 1 is always plus 1. Group 2 is always plus 2. Group 16 is always minus 2, and especially oxygen. Oxygen is one of the standards that you like to use. Hydrogen is the other one. H plus, it's always 1. Group 17 is always minus 1. And then you have these notable polyatomics that you want to be aware of. Hydroxide minus 1, nitrate minus 1, sulfate minus 2, carbonate minus 1, and ammonium plus 1. So these are these notable standards that you want to be aware of. And so you'll use these to mathematically determine the charge on elements and atoms in a compound. So let's take a look at an example of an oxidation-reduction reaction. Again, oxidation reduction takes place when the copper metal reacts with oxygen in air to produce copper oxide, as an example. So we're looking at the oxidation of copper from copper in its 0 state. How do you know it's 0 state? Because it's in its elemental state. And it's being oxidized to copper plus 2. That means 4 electrons were transferred. Why? Because we must be able to write a balanced equation for this reaction. Oxygen is being reduced from its elemental state of 0 by gaining 4 electrons to form 2 atoms, 2 molecules of oxygen minus 2. Why? Because the reaction has to be balanced in terms of its atom count and its electronic count. When we summarize this equation by using classical math methods, we obtain 2 molecules, 2 moles of copper, plus 1 mole of oxygen, giving us 2 moles of copper 2 oxide. It is copper 2 oxide because we use the transition metal rules for naming this. And in this case, copper has a plus 2 charge on it. And therefore, we denote it with a Roman numeral. So, we went from 0 charge on the copper to a plus 2 charge on the copper. We went from a 0 charge on oxygen to minus 2 charge on it. Now, when we carry out this process, copper is the reducing agent because it causes the reduction of oxygen. Oxygen is the oxidizing agent because it causes the oxidation of copper. So, in other words, the species that underwent oxidation is the reducing agent. The species that underwent reduction is the oxidizing agent. So let's repeat that. Copper is the reducing agent because it caused the reduction on O2. Copper itself underwent oxidation. Oxygen is the oxidizing agent because it caused oxidation of copper. Oxygen is itself, therefore, the species that underwent reduction. Got it? Let's take a look at another example of oxidation reduction. In this case, we have zinc plus copper 2 sulfate giving zinc 2 sulfate plus copper metal. In this reaction, zinc goes from a 0 state to a +2 state. Copper went from a +2 to a 0 state. Zinc was oxidized and copper was reduced. Zinc is oxidized to +2, therefore zinc is the reducing agent. Copper was reduced to a 0 state, therefore copper +2 is the oxidizing agent. Be sure when you name the oxidizing or reducing agent that you tell the charge. That is very important. So it's not just zinc, it's zinc 0 is the reducing agent. Copper +2 is the oxidizing agent. So we take a look at oxidation numbers. We'll show you how we derive our answers for neutrality. We note that zinc is 0, and in the case of copper 2 sulfate, we start with sulfate because sulfate is a standard at -2. Copper is a transition element, therefore its charge might vary. So we start with SO4 as a standard at -2. Therefore, for electronic neutrality, copper must be +2. We do the straightforward math. +2 plus a -2 equals 0. We go to the right side of the equation where we have zinc 2 sulfate. Zinc is transition, therefore it could have a variable charge. So we start with the standard of sulfate, which is always -2. So we have -2. Therefore, zinc must be +2. We do the straightforward arithmetic math. +2 plus a -2 equals 0. And since copper is solid, that means it's in its elemental state, it is 0. Therefore, this equation is balanced in terms of its atoms and is balanced in terms of its charge. So let's practice these oxidation numbers. Let's assign the oxidation number to the following ions. Keep in mind there are standards that we will use to help know how to assign the others, and we use simple math, arithmetic math, to do these problems. Ready? Now, we have lithium oxide. We know it's lithium oxide because lithium is in group 1. It is metal with oxide. It is therefore an ionic compound because we have group 1 with group 16, ionic compound. So we have this ionic compound. So since oxygen is always the standard at -2, we assign the -2 to oxygen. We note that we have 2 atoms of lithium. Therefore, for electronic neutrality, straightforward math, 2 times +1 gives me a +2. Therefore, the charge on lithium must be +1 since oxygen is -2 and we have 2 atoms of lithium. To balance it out, add a +2. So +2 minus 2 gives me electronic neutrality. This is how you do all of these problems. Find the standard first, look at the math, make sure you multiply the subscripts, time the charge. In the case of oxygen, in lithium oxide, we only have 1 oxygen, so it's 1 times -2 for -2. Therefore, in order for the positive charge to work out, we have to have a +1 on lithium. Let's do another problem. Nitric acid. In this particular case, we basically have 2 standards. Hydrogen is always +1, oxygen -2. We put in the standards, and that gives us right now a charge of 3 times a -2 for -6. And we have -6 plus the 1 hydrogen gives us a +5. Therefore, nitrogen is assigned a +5 by doing straightforward arithmetic math. So hydrogen then has a +1, nitrogen has a +5, oxygen has a -2. Let's do a charged ion. In this case, the ion is a chromate ion. It has a -2 charge. Therefore, after we complete our math, we must be left with a -2 charge on the polyatomic ion. So here's how the math works. We have the standard at -2 for oxygen. 7 oxygens times a -2 equals -14. Therefore, the positive side of this must equal to what? +12, in order to have a net of -2. Since we have 2 chromium atoms, that means chromium must be a +6, which gives us 12, so that we can have our electronic charge of -2 on the chromate ion. Therefore, chromium has a +6, oxygen has a -2 in this polyatomic ion. And there you have it. That completes Lecture 3 of Chapter 4, Stoichiometry and Chemical Reactions.